Well, here we are again. We just developed some general ideas relating the slope of a function to its derivative. And what we want to do now is just start developing individual rules. We're going to start with the power rule. Remember, any dependent variable can be kind of a complicated function of different components, each of which contain the independent variable. Let's say y, a function of x. X could be raised to some power. We could have a sum of terms in x. We could have x being a function of some other variable, and so on. So we're going to talk about some of those different forms that x can take on and how we would differentiate them. So if we have a simple function like y is equal to x squared here, let's take a look at that first. So we're dealing with the power rule, x raised to some power. Dy dx is the derivative, and this is defined. The derivative is basically defined as the limit as delta x goes to 0. We have delta x in the denominator here of delta y, delta x. So this is just our slope, but we're looking at the slope, and we talked about this in the last video. We're looking at the slope in the case that delta x goes to 0. We took a couple examples where delta x was separated by, delta z in that example, was separated by 1 kilometer and then 200 meters. So if we're evaluating y is equal to x squared, following this formula here, we have the derivative then is equal to the limit delta x goes to 0 of x plus delta x squared, that's our y, at delta y, minus x squared over delta x. And multiplying this term out, this expression then becomes x squared plus 2x dx, delta x, plus delta x squared minus x squared over delta x. We can see that there are some terms that are going to cancel out. These delta x's are going to cancel out. We're going to lose one of these. These two x's are going to cancel out. So if we look at the cancellations here, dividing through by delta x, we get basically evaluating the limit, in the limit that dy dx up here is equal, in the limit that delta x goes to 0 is equal to 2x plus delta x, but delta x is going to 0, so it's just equal to 2x, or 2x over here. So if we try x to the fourth, it's a little bit more complicated, but let's see what happens there. So multiplying out x to the fourth is a little bit more laborious, a little bit more tedious process. If we do that, sit down and multiply that out, we get x to the fourth plus 4x cubed dx plus 6x squared dx squared. We can see that the powers of x are going down, 4, 3, 2, 1, and so on, and that the powers of delta x are going up, 0, 1, 2, 3, and so on. That's doing that by hand, multiplying that out is a rather tedious process. So I'm kind of going off on a bit of a tangent here, no pun intended. But we'll take a look at Pascal's triangle and see how that might help you out if you had to do this for if it was something you did more than once. It might be something useful to know. If we look at Pascal's triangle, we've got ones down along the sides of the triangle, and then we have some unusual looking numbers filling up the interior of this triangle. Notice that at the apex here we have 1. The first row is 1 and 1. The second row is 1, 2, 1. This 2 comes from the addition of these two numbers. We get 2. The 3 comes from the addition of these two overlying numbers on the hexagon here. And we get a 3 again by summing these two numbers, 2 plus 1, we get 1, and so on down through the triangle. So 1 plus 3 is equal to 4, 3 plus 3 is equal to 6, 3 plus 1 is equal to 4, and so on. Well, you'll notice that those are the exponents, or those are the coefficients of the terms that we have in that product. So we've got 1x to the fourth plus 4x cubed, you know, as the powers descend for x's and they increase for dx. We get 4x cubed dx plus 6x squared dx squared, and so on. So if you find yourself having to determine what x plus dx to the fifth is, well, it would be x to the fifth plus 6x to the fourth dx plus 15x cubed dx squared, and so on. So using these coefficients. So that's a handy, hopefully a useful tangent to go off on here. Now taking a look at this expression, remember that the dy and the dx, their differential changes and they become infinitesimally small, very small. So so we know that these terms are going to go to 0, and if dx is, you know, using this as an example, let's assume that dx hasn't quite made it to 0 yet. So we have dx is equal to 0.0001, or 1 times 10 to the minus 4th. Dx squared is 1 times 10 to the minus 8th, 4 orders of magnitude smaller. Dx cubed, 1 times 10 to the minus 12th, and so on. Dx fourth, 1 times 10 to the minus 16th, and we're 12 orders of magnitude smaller than dx. So I think you probably wouldn't argue if we said, okay, well, let's just kind of ignore these terms. It's going to be a small error that we're left with. And dx squared, orders of magnitude smaller, dx cubed, and so on. So we'll just ignore all those terms in this expression where, you know, dx to the n, where n is greater than 1. And that gives us an expression then that looks like this, where we have y plus dy is equal to x to the fourth plus 4x cubed dx. So we've just gotten rid of all these terms here because dx squared, dx cubed, dx to the fourth are so much smaller that we're just ignoring them. Now, since y is equal to x to the fourth, we know that these y's are going to cancel out. We have an x to the fourth there, an x to the fourth here. We end up with dy is equal to 4x cubed dx. Okay, so now we're going to divide both sides of this expression by dx, and so that we get dy dx is equal to 4x cubed. So our derivative then is dy dx, where y was equal to x to the fourth, is equal to 4x cubed. What I'd ask you to do now is, can you see any relationship between the original function and its derivative? So we already talked about this one. We could see that the delta y, delta x, the slope was 2, and it was linear, so it varied linearly with x. So notice that if we take a look at x squared, we're just taking the exponent, bringing it down in front of the x, and then reducing the exponent by 1, so we get 2x. Let's see if that rule applies here. Bring the exponent down in front of the x. We get our 4 here. We get x to the 4 minus 1 power, 4x cubed, and that's just exactly what we got. So we have a general rule that we can use, and so that factor before x is just the power that the function was originally raised to in both cases, and we reduce the power of x by 1. So that we get y is equal to x squared. Its derivative is just equal to 2x. For y is equal to x to the fourth, its derivative is just equal to 4x to the 4 minus 1, or 4x cubed. So in general, we have this general rule, nice, easy rule to remember, if we're differentiating an exponential or a power, or x raised to some power, you have dy dx for y is equal to ax to the n. We bring the exponent down in front. We reduce the exponent by 1, and our result is then n times a. This constant here, it just carries through. We'll talk a little bit more about that later on, but n a x to the n minus 1. And so these constant factors in here, they just carry through the differentiation, and this also happens when we add a constant to a function. Well, it's not the same thing, but when we add a constant to the function, it basically disappears because its derivative is equal to 0. So if we have x squared over here, let's say, plus some constant, its slope is still going to be the same. That function may look like this. It may be elevated, but the slope is going to be the same. For something that looks like y is equal to ax squared plus b, then the derivative of b is just 0. So we just end up with 2ax. So we'll just take a look at this in a little bit more detail. Just expand on that idea. If we have y is equal to ax squared plus b, we have y plus dy. Just substitute x plus dx for x. Gives us a times x plus dx squared plus b. And we have y plus dy is just going to be equal to, carry out this multiplication, a times x squared plus 2x dx plus dx squared plus b. And just going through the steps and rearranging terms. Remember, we're just ignoring these dx quantities that are larger than where the exponent is larger than 1. And we're grouping our terms, so we bring our b back over here. This gives us our original y. And then we have this leftover term in here, 2ax dx. Remember, we have y over here. This is y. So they're going to cancel out. We divide through by dx. We get dy dx is equal to 2ax. So here's another way of doing that. You have dy dx is equal to dax squared. We're kind of jumping ahead here because we're going to be talking about the sum rule. And so we're kind of taking in advance, jumping in advance into an application of the sum rule. We've got a function which is basically the sum of that function ax squared plus b. We just distribute the derivative operator through the sum. So we get the derivative of ax squared dx plus the derivative of b with respect to x. B is a constant. This goes to 0. We just have the derivative of ax squared dx, which is just equal to 2ax. So we have a line with a slope equal to 2a and a 0 intercept. Something else not to get fooled by is, if the exponent is negative, there is a special case that we have to worry about when we'll come back to that and talk about it later. But when the exponent is negative, we do the same thing. Bring the we have a function ax to the n. We'll bring our n down in front, reduce the exponent by 1. So if y happened to be ax to the minus 1 power, we'd have minus ax to the minus 2, reducing the exponent by 1. So we'll talk about the sum rule in more detail in the next time. So see you on the next video.